Alright, did you guys, you still don't have enough? Of the lab? Nobody, no, one more of the lab that you said? Alright, I'll get another one of the lab if somebody by chance picked up an extra. I'll get it shortly, okay? I just don't have it right in front of me. Alright, this was my love note to you this morning. Because I basically all I thought was about your comments the entire night. Thank you. But a lot of you guys gave me great feedback, and I appreciated it. And when I texted out, like, you know, provide information, email or text. And I was just thinking about how I could approach you in a way that you don't absolutely hate me. It's a good love-hate relationship we can have, but at the same time, I'd rather be more love than hate, so I kind of have to balance that with you guys. So I will be honest with you. It's hard.
Teachers, please set your recycling bins outside your classroom door. Thank you.
It's hard to teach my highest flyers of the entire school. Literally are the smartest people in the school. You all want to do incredibly well, and I applaud you for that. I wish you could help you on your back. You will do incredibly well. You'll get what you want, but it sometimes takes more time than normal because we do have a year, right? So you're going to be seeing this undulating roller coaster of like, oh my gosh, I don't know what I'm doing. And then, okay, yes, I know what I'm doing. And it is a lot of application, right? So it's no more like, what's the definition of Bronsted-Lowry, right? It's no more, what's hydronium's formula. So, you know, one test had a lot of background information, making sure we're all basically on the same page from honors chem up until AP chem. The application on that was pretty low level in terms of like what you would expect from an AP exam. So what I try to do is, this is what's been successful for me in the past, you always get the high scores in the end. Most people go to college and go, piece of cake if they have to take some portion of chemistry again. But what I'm just trying to relay to you is that I want your feedback. I'm going to use it where I can, but I can't use it immediately all the time because I still have to think about the big picture. So I know at the end of the year, April, you guys are going to be like, okay, we're done learning, we're reviewing. And so if I start to move days like, okay, we need extra day here, and then here, and then here, and then here, I can easily eat up 2 weeks by doing that because we have about 10 units. So if I give us one more day in every unit, that's 2 weeks. That leaves us with 1 week of review before the AP exam. And most people would be like flipping the table, right? It just wouldn't be the best move for us as a whole family. And in the end, I want you still to, of course, enjoy everything we're doing, but you will feel a little bit of that pressure because you normally haven't probably been as challenged in other courses. So in terms of application, we'll try to do more of that, and I'm trying to balance where our labs fall in terms of application where we apply just in class like through problem sets or through just paper-based practice. But as you saw, and those of you who have not taken the test, spoiler alert, there's some lab application questions, hence why we do the number of labs we do. And the other side of that is, as an AP chemistry certified teacher, we have to spend 30% of our year in the lab. How many days a week is that? So 1 to 2 days in lab, right? So because 1 day in the lab would be 25 or 20%. 2 days in lab would be 2 out of 5, 40%. So we kind of have to flux between that, which is why I do make sure that we are practicing, doing our pre-labs together, we're planning labs together, and so forth. So we'll talk some more, but this is at least the thoughts I want to get out to you guys before I move on to our next unit. Okay, so you guys picked up the papers. In terms of what you guys read last night, try to talk to the person next to you and tell them what you think the point of what we're doing is. The point of what we read. Alright, come back to me, come back to me. Stay focused. Alright, so, Taz, what do you think, like, some of the main points of what you're reading was about last night? So you said oxygen, what? Okay, so oxygen can serve as a oxidizing agent, but it doesn't have to. There's many, many others. What else? Chase, what do you think was important for reading last night? Deep thoughts over there.
Yeah. Just like defining how like the whole thing is being chart, or no, like the individual ones, like how we predict them?
Okay, so basically reflecting on how individually a polyatomic ion or a compound as a whole can be neutral, but individually they still have some sort of pull on electrons in their individual bonding situation, which we then say has a charge, but we're going to try to eliminate the use of charge in terms of, okay, charge is one thing and oxidation state is another thing, but they're super, super similar. And then and with respect to that, it's all about electronegativity. Okay, so we're going to speak to that some more. Mary, one more thing. Well, I can tell you guys, we've been doing oxidation reduction reactions this entire year so far. Every single reaction we've done except for double replacement has been oxidation reduction. We just have never respected that side of it. We've just said, hey, let's balance this reaction and predict the products. So that's basically what we've been doing, but now we're going to actually look at that a little bit more in depth. Before we do that, though, I want to show you like probably one of my favorite comics of all time. This one right here. Somebody tell me why that's funny. So say it for me. No. All right. Well, you guys are awake today. All right. So we're gonna first focus. It has 11 electrons. Okay. We're gonna focus on just the basics first, and this is kind of what you read about. I'm just gonna repeat some of the items. You should probably be taking notes with me, right? So I'm gonna repeat and like kind of explain some of the things you guys already learned about, and then we're going to apply that to balancing reactions. So the first 2 days of this unit are just balancing reactions. Sounds pretty simple, right? But we're balancing reactions with respect to not only matter, like the number of atoms, but also charge, which is the number of electrons that were exchanged, or the number of electrons that were freely floating around between two different atoms. So the basics here, oxidation reduction, we tend to call those redox reactions. That was one of the questions in your, like this first or second question in your active reading guide. Just keep those out for me. I'll see those as I can today. Oxidation reduction reactions have to occur together. So we always call them oxidation reduction or redox as a whole because they cannot occur independently from one another. Oxidation and reduction, one is the loss of electrons, the other is the gain of electrons, so they have to occur together. So it's basically just us honing in on how the electrons are transferred between atoms or elements within a reaction. And the real big deal about all that is just simply us recognizing that there is solely really one thing that's causing reactions to occur, and it's the drive to gain or lose electrons. So electron configurations, that's what I mean by config. Electron configurations help us predict reactivity, or help us see how, in many cases, if you're not quite to octet, meaning you don't have 8 valence electrons in your outer shell, you're going to get it somehow. Or if you don't, you're going to drop off electrons until you go back to your last octet. So there's some background information to this, but we're specifically just speaking to it from the trends that we see across electronegativity. So one of the other main points in oxidation reduction reactions is if the electrons are lost from one entity and gained by another, they never disappeared. So it's going to follow the same idea that matter or energy, both of those can neither be created nor destroyed. Electrons are a part of that because technically electrons are matter. They have a wee bit of mass, but we usually ignore that because it's so tiny. We don't include that like in the atomic mass of atoms and much, and not even at this level. So they are matter, so we have to account for the electrons lost and the electrons gained, and they should be equivalent due to the law of conservation of matter. So LOCM's law of conservation of matter. And the whole application side of this is actually broad. It's very, very broad. It's literally in every reaction we do except for double replacement. And it's a lot of times what's basically how our body functions. So biochemistry is very much oxidation reduction. Raise your hand if you think you might take AP Bio next year. You will have a whole unit on oxidation reduction with respect to photosynthesis and cellular respiration, and all those functional groups with the organic side of things. They'll all be included in that as well. So most people take chemistry before they take biology because chemistry drives biology. Biology doesn't do anything for chemistry. It's the other way around. So the relevancy comes into oxidative phosphorylation, which is a term that most people don't know. It's fat burning, so if you exercise, your body's undergoing oxidative phosphorylation all the time. And oxidative, that word, is because it's an oxidation reaction. And then there's some other ones. Metabolism in general is an oxidation reduction process. Photosynthesis, cellular respiration are a lot of ideas that are a lot of processes that are driven by oxidation reduction. Thumbs up if I can move on. Okay, so this is like kind of a background piece that will try to put everything in context so that when you're reading scenarios, you're like, oh, this is just background information, but it applies because these reactions are prevalent in this particular, context. Okay, so this is the background in which is related to what you guys read last night, so forgive me if it's too repetitive, but I think if I can say things twice, then you guys should be good from there. So oxidation states or oxidation numbers is what I mean by OX number. So oxidation states or oxidation numbers are numbers that we assign artificially to elements. So I'll let you take a minute and read that first so that you can synthesize what you're writing down. So when we say something has a charge, we are assuming that it has already attained a set of electrons or lost a set of electrons, which makes it an ion. So I'm going to start down here. Charges are generally what we use to talk about ions or components of an ionic structure. So they have actually exchanged electrons. They have a negative charge or they have a positive charge. So that's generally very true for metals, right? So metals are low in electronegativity, and they do not want their electrons. They want to give up 1, 2, or 3 electrons because they have lower than 4, not even close to octet, so they're never going to gain 5, 6, 7 electrons to achieve octet. They will always lose. So with respect to that, that's why we always say ionic compounds are between metals and nonmetals or metals and polyatomic ions, because they will lose electrons. But what about all those covalent compounds that we come across? They don't take on extra electrons or lose extra electrons. They share electrons. But we have to find a way to track electrons where they are in a reaction, even with respect to covalent stuff. So what we do is we artificially assign a charge, but we're not really calling charge, we're calling an oxidation state. We artificially assign that to every element in a compound. And we do that by way of electronegativity. So if you're in my class, and maybe you make them, but I think he maybe taught you guys this. Can you guys do this for me? Right hand goes, you got 2 little L's, okay? Right hand goes down. This is the atomic radius trend generally. And then flip your other hand around. And so you have like a little picture. Right hand, hold your right hand up, drop your right hand down. So your right hand is pointing to the left now. Help the person next to you. I know it's the morning. And then your left hand goes like this. Okay. So your right hand represents the strength of the atomic radius. Your left hand is representing arrows that point like the arrows here on the board. And the electronegativity trend is increasing as you go up a group and then increasing as you go right across a period. So if you're in my class and we did periodic trends, this is what we did to help you remember the trends themselves. So, but regardless, this is the electronegativity trend. So who is the most electronegative element? Fluorine, way up here. And so everything kind of halogen related is going to be very electronegative. So if they have the chance to take electrons, they will. And that would give them a -1 charge, or if they were an oxygen's group, a -2 charge. But what we have to say is, what if I have a position where I have 2, let's say, oxygen and fluorine, okay? I have 2 nonmetals. Well, They have to share electrons. That's what covalent bonding is. They have to share. But what we do is we artificially assign the more electronegative one with the charge as if they did actually get the electrons. So in a bonding situation, we're assigning them to the more electronegative element. So this is very useful in molecular compounds. Molecular means what? Say again? Covalent, right. It means a compound that is not ionically bound, so it's a covalent compound. So what we generally see a lot of is in the metal side of things, and these are all the transition metals down here. In metals, they just get the charge we would have assigned them. If you're in group 1, you get a +1 charge or +1 oxidation state. If you're in group 2, you get a +2 charge. You get a +2 oxidation state. If you're in group 3, you get a +3 oxidation state. But it's really fuzzy when we get to the non-metals, so we're going to talk about prioritizing our oxidation states in a second. You do have a list of valence charges from the summer packet, but there's no way you will remember them all. Absolutely not. But I just wanted to show you that they all have different colors. So in particular, manganese, do you see manganese right here? How many oxidation states can it have? Do you see it right here in the middle? 1, 2, 3, 4, 5, 6. The 2+ oxidation state is kind of a pinky peach. The +7 is like a magenta, kind of purpley red. And so these things actually we can see the oxidation states because they have a different color than their other oxidation states as well. But that's only really prevalent in transition metals. Those are the only things that have true colors. Okay. The only other one I was going to show you was vanadium. It has like 4 different colors. I don't have any vanadium to show you, but it's actually really cool when it goes through those. Okay, so these are your priorities. You wrote down some of these in your reading guide, but I'm making sure that you're clear on what this is referring to. So when you are assigning oxidation states, you have to prioritize who you assign first. That's what this list is. When you assign oxidation states, you have to prioritize who you assign first. So I'm going to start with the priority list down here first, and I'll go back up. I'll let you guys read and write first then. I'm going to scroll back up to this in just a second, okay? So whenever you are prioritizing, since that's what I'm talking about first, you have to recognize that the metals, meaning group 1, group 2, and group 3, they will definitely, and I say group 3, but it's really just aluminum, they will take on a loss of, they will lose electrons. They will lose 1, 2, or 3 electrons. So this is very much just like their ion charge. Their oxidation state is the same as their ion charge. Hydrogen, well, if we had to assign a charge to hydrogen, we know it's not electronegative. We know it's going to lose 1 electron. This oxidation state is the same as its charge if it were to form an ion. Some of them are very, very similar. That's why we kind of say tomato, tomato sometimes. Fluorine will absolutely, if in a situation and you have to compare two elements to some oxidation state, it will definitely be the one that's got the higher electronegativity value. So increased electronegativity means that we would assign it to have an extra electron, and that's fluorine's -1 oxidation state there. Oxygen, similar story. It's similar to the charge if we were to assign it as an ion, but the only thing where these things don't actually follow these 2 priority rules are if O and F are together, oxygen and fluorine together. We'll do an example with that in a second. And again, the non-metals that are close to octet will definitely gain electrons 1, 2, and 3, which would then give them a -1, or a 1 negative, a 2 negative, and a 3 negative oxidation state. And I will try my darndest to do this always, but you're supposed to write the number and then the sign afterwards for an oxidation state, So like 1 plus is an oxidation state, but plus 1 is a charge. And that's how they differentiate it when you're writing them out, but I will not hold you to it because I'm horrible at making that happen myself. So I would probably say plus 1 because that's just so natural versus 1 plus, because it's kind of weird to say that. So these are our priorities. This is how we will assign oxidation states. This will make more sense when we apply this. The other rules that were up here are if you have a compound and the compound is a neutral compound, overall, all your oxidation states must the sum of the charge, or the the sum of the oxidation states must equal the charge of the individual, like polyatomic, like this one. What's their overall charge for ammonia? Ammonium. Say again, plus 1, right? So the oxidation states must add up to that. Or something like ammonia, which is neutral overall, we have to have our oxidation states add up to be 0. If you have a free element, like a diatomic molecule, do you guys remember your diatomics? The big 7. So where do I start with the big 7 at? Nitrogen, oxygen, fluorine, chlorine, bromine, iodine. The big 7 and hydrogen are all diatomic molecules, and they would have a 0 oxidation state. And then monatomic atoms, like simply sodium, iron, copper, they're monatomic, meaning they're one atom, but they're not charged yet. They're simply neutral. They're like their solid states. Those would have an oxidation state like or as a 0. And then a monatomic ion would just, its oxidation state would be its charge. So if I had sodium ion with a plus 1 charge, what's its oxidation state? 1 plus, right? What's the oxidation state of copper 2? That's a 2, plus 2, 2 plus. So those charges are their oxidation state as you go. All right, I can go back here if I need to, okay? So let's apply some of this information. Let's start with sulfur, or what's the name of this, by the way? Sulfur trioxide, okay? So prioritizing, who's at the top of your priority list? Okay, not sulfur, right? So oxygen it is. So oxygen's going to get a what oxidation state? -2 or 2 negative, right? So I'm going to just write that right above the atom. But what you now have to accomplish is math. Easy math, though. -2 times 3, because there's 3 atoms of O. That's what? -6. So this total on this side is -6. Okay? That's going to be negated by sulfur. So what does sulfur's oxidation state have to be? Just a +6, right? So you do put a sign on it so I know that you know if it's positive or negative. So basically the oxidation state of oxygen is -2, the oxidation state of sulfur is 6 plus, but collectively together, what do they sum to be? 0, because of the 3 multiple of oxygens. Yeah. It means that when I said 0 like this, I mean that the oxidation states sum to the overall charge of sulfur trioxide, which is 0. No. It just is making sure that you have your electrons assigned appropriately inside of the compound. But what we will see over time is that sulfur can change its oxidation state as it forms a product. That means it reacted because it changes its electron configuration. No, the 0 just means that the sum is 0, that the overall compound is neutral. That's it. Okay. So let's go ahead and do phosphate. Okay. So who's priority, phosphorus or oxygen? Oxygen, so it's going to get a 2 negative oxidation state. Overall, 2 times 4 is, sorry, -2 times 4 is what? -8. So basically what we have here is phosphorus plus 4 times 2 negative equals 3 negative, or -3. So phosphorus, I got to figure out its oxidation state. If this was -8, but the total was -3, what's phosphorus? Say again? +5, right? Let's be confident in what we're saying, okay? So yeah, +5 is the phosphorus's oxidation state. Who's with me? Okay, let's do a couple more. Let's do oxygen and chlorine with an overall -1 charge. Okay, so who gets priority here, oxygen or chlorine? Oxygen gets a -2, so then what does chlorine have to be for the sum to be -1? Say again? +1, right? Because we need a -2 plus 1 to equal overall charge of -1. Okay, you guys try sodium hypochlorite. All right, where did you guys start? With sodium. Okay, sodium's our metal, which is in group 1, so it's going to have a +1 oxidation state. And then who's your next priority? Oxygen got a 2 negative or -2, so then what's chlorine have to be? +1, and that's going to give us a total of 0 because overall there's a neutral compound here. Okay, let's do one more. Oxygen, fluorine. Go. Has to be. Who's your priority here? Everybody, who's your priority? Fluorine's your one that has to have a -1 charge or -1 oxidation state because it's got a high electronegativity or the highest. So if this has a overall charge of what between fluorine and it's 2 of them here? -2. What does oxygen have to be? A +2. So that's an anomaly to what we normally do, but it's because fluorine will win in the electronegativity battle. Fluorine is more electronegative. Okay? Yes, ma'am.
So the order that you're putting priorities in, is that the order?
That's the order that you start assigning. Yep. So there's one more thing I didn't do down here. There are exceptions to some of the rules. So these are the exceptions that you should be aware of. One, if hydrogen is an anion, meaning it's in the back of a compound, like calcium hydride or calcium hydride, something like that, then we have an issue, right? It's an anion. You can't give it a positive oxidation state. It's a negative oxidation state. Peroxides, each of those oxygens in the peroxide situation actually have an oxidation state of -1. So an example of something like that would be potassium peroxide, where we would have overall peroxide with a -2 charge, but each of those individual atoms of oxygen have a -1 oxidation state. Super oxides, which is very rare, we will likely never encounter those, but they have it's O2 with a -1 charge. So how do you split a -1 into 2? You half it, right? So normally we won't encounter that too frequently, a non-integer oxidation state, but it does exist. So if you ever come across it, don't be like, oh, this can't be right, but it will be fairly rare when we come across that. So you can have non-integer oxidation states. All right, so peroxide gets what for its oxidation state? Negative, or -1, right? Negative, or 1 negative. All right, so let's go do some more practice with respect to a reaction now. So I'm going to try to pick up the pace now that you guys are with me. So before I do reactions, quick review. Oxidation is loss of electrons. Here's how I've remembered it since I was in 10th grade, or 11th grade, I guess. So oxidation is loss, O-I-L. Oxidation is loss of what? Of electrons. Okay, so we're going to call this whole ordeal oil rig. Okay, some people call it Leo Gur. Leo goes Gur, like a lion, but I don't like that one. I like oil rig. So oxidation is just the process of losing electrons. As you lose electrons, you naturally become more positive because what charge does an electron have? Negative. So what it looks like over the course of a reaction from reactants to products is that you increase in your oxidation state. So you might go from 0 to +2. So if you go from a 0 oxidation state to a +2 oxidation state, how many electrons did you lose? 2. Okay. So that's the idea of what oxidation is. Rig, or reduction is gain of electrons. Remember that we're talking about electrons still. If we're gaining electrons, well, we're gaining negative charge as we accomplish our reaction. So I might go from a +2 oxidation state to a -1 oxidation state. How many electrons did I gain? 3. So I went from 2 to 1 to -1. So I gained 3 electrons. So that's just those are some definitions to get us started for applying this. So oil rig. Okay, oil rig. Oxidation is loss of electrons, reduction is gain of electrons, and that definitely impacts your oxidation state. All right, so remember again, these have to happen simultaneously. They cannot occur independently because once one is lost, so for example, these electrons here, these are lost through the reaction process. Where do they go? To the other half reaction, right? So this half of the reaction is losing, but it's actually not just losing it to nowhere. It's losing it to the ones that are gaining. So they have to happen simultaneously. They cannot occur independently to each other. Give me thumbs up if I can move on. Okay. So here's one example, or two examples of oxidation reduction reactions. And here's what I would expect that you'd be able to do. You look across and you have to assign oxidation states. We see this sodium. It's a free element, also a monatomic atom. What's its oxidation state? 0. So we always write oxidation states on top, okay? Chlorine, free diatomic molecule. 0, okay? We have sodium chloride. Who do you want to assign first? Sodium gets a what? Okay, and chlorine gets a, say again? -1, right? So sodium and chlorine together basically negate each other to give us an overall neutral compound. So after you've assigned them, you now just draw brackets to indicate changes here. So sodium went from 0 to a +1. So I'm bracketing that off to show that it's changed and I'm tracking the changes. And you guys have to tell me, oxidation state went up or down? Up. Okay, so did it lose or gain? Lost how many electrons? 1. So it lost 1 electron. So I like to write that kind of as I think it, and then you're going to tell me, is it oxidation or reduction? So it sounds weird, right? It's not, you're not losing doesn't mean you're reducing. What's your little acronym? Oil. So oxidation is loss. This is an oxidation reaction on the first half. Okay, and then chlorine going from 0 to -1 did what? Gained, right? So Rig, it's going to reductionist gain. How many electrons did it gain? It looks like 1, right? So here's the fact though. It looks like it gained 1, but overall we have 2 sodium atoms and 2 sodium atoms. So though we look at the oxidation state individually as an individual atom, there's 1 electron exchange, but there's 2 of them overall. So overall, I actually have 2 electrons that are unaccounted for. So where do I find those unaccounted electrons? You guys see the chlorine has 2 as well? 2 chlorine atoms and 2 fluorine atoms. Each of them individually gained 1 electron, but overall there's 2 electrons that are gained there. So they must be equivalent because of the fact a law of conservation of matter. Yes, ma'am.
Do the states of matter have anything to do with oxidation reduction processes?
Not the process, but it will be with the assignment of the oxidation state. Because a lot of times, like if I'm in aqueous solution, it's an ion, but if I'm in solid or liquid, sodium would be a pure metal still. So it'd be a 0 versus a +1. Okay, so you guys do this one. Do hydrogen, oxygen, mix water. All right, CJ, what did you assign hydrogen gas here? Okay. Darcy, what did you assign oxygen here? JT, what did you assign hydrogen here? And Margaret, what did you assign oxygen? 2-. Okay, sorry, I'm going to keep screwing up the positives and negatives, guys. So your hydrogen goes from H0 to H +1. Marcus, what happened?
It lost electrons.
Okay, so loss of electrons means what? It was what? Oxidized or reduced? Oxidized, oil, oxidized, okay? Jillian, what happened to oxygen here? So gaining 2 electrons means it's reduced or oxidized? Reduced or oxidized? Reduced. Rig, and then we gained electrons. We know that they're balanced, one, because hopefully they're balanced. The reaction itself is balanced, so we can see that there's an even number of atoms on each side. And if that's the case, and they're losing 1 electron at a time, then in that case they'll also be balanced in terms of charge. So this is R2 and R2, each of them losing 2 electrons. So overall, how many electrons is lost? Gained by oxygen? 4, right? So there's 2 of each of the oxygens, each of them losing 2. So overall there are 4 electrons gained. And then looking at hydrogen, how many hydrogens are here? 4 and 4, each of them losing 0 to losing +1 electron. So overall I have 4 times 1, which is 4 electrons that are lost. So they are the same electrons that are lost and gained. We're just tracking them by oxidation states. Can I move on? Okay. So what we try to do instead of looking at the whole reaction is we actually tend to break them into 2 half reactions. These are literally called half reactions. So sodium overall from this first example had a 0 oxidation state and then a +1, but to balance this half reaction out, you must show where the electrons exist now. Well, they were lost because it's an oxidation half reaction. So if it's an oxidation half reaction, electrons are lost, and we show those 2 electrons that are lost as released electrons as a product. For the second half reaction here, you have a what kind of reaction? Oxidation or reduction? Reduction, right? So this was the one we just did previously. This was a 0 and this was a -1. But overall, 8 gained electrons. Well, to show the gaining of that is you have to add it in the reactants. So we show a gain of electrons in the reactants. And we show a loss of electrons in the products. So reduction, reactants, reduction, reactants. You can see the electrons are gained as a reactant. So these are called half reactions. What do you notice based on, because these are happening at the same time, right, simultaneously, what do you notice about the number of electrons that are lost and gained? They're the same, right? So the electrons are balanced and the atoms themselves are balanced. So we're going to call that mass balance and charge balance. Mass is the number of atoms, like sodium and sodium, chlorine and chlorine. And then charge balance is the electrons and electrons that are the same throughout. Thumbs up if I can go on from here. All right, almost there. So we're going to start after, so since we know the background, we know the basics of how to assign oxidation state and also look for charge balance and mass balance. We're actually going to do a full reaction now and balance it by oxidation state change. From there, we're then going to go to acid catalyzed reactions and balance in an acid, which has a slightly different approach, but it's much more common after this. Okay. All right, so this is just terminology. You guys wrote down oxidizing agent and reducing agent in your reading guide. But again, terminology, it's opposite of what actually is occurring to itself. So the agent that oxidizes is not itself oxidized. The agent that oxidizes something else itself is reduced. It's an odd kind of way to describe it, but sometimes you'll see this specifically throughout the year. Some of these things you may never see in the AP exam, but you know, whatever. So oxidizing agent is one that causes oxidation by forcing electrons to be lost. But in that respect, it's going to cause itself to be, it's causing electrons to be lost from another atom. So it's basically pulling electrons towards itself. So itself is going to be reduced. Does that make sense? It's stealing electrons from something else to reduce itself. And then vice versa for reducing agent. It's going to be forcing electrons off of itself, right? Forcing a release of its own electrons. Of its own electrons to then oxidize, or then to, oxidize something else. Reduce itself, hold on. Cause reduction. Oh yeah, sorry, itself is oxidized because it lost electrons. Releasing its own electrons will reduce something else, which is why we call it reducing agent. Itself being oxidized since it lost electrons. But that's just the definition of oxidation and reduction. So occasionally we will identify oxidizing agents and reducing agents in a reaction itself. Okay, some of these are definitions from your reading guides. All right, so let's look up here for the oxidizing agent and the reducing agent. Assign your oxidation states first. Write your reaction out and assign your oxidation states. Emma, what do you say for lead and sulfur oxidation states? Take a stab at it. What do you look at sulfur again? What group is sulfur in? 6. So I'm going to point to the wall over here, guys, if you need it. 2 negative, right? So in the case of lead, lead's not on our priority list at all, so I would assign that second. So looking at sulfur being in group 6 is going to gain 2 electrons to be like a noble gas electron configuration if it were to have the highest electronegativity. So it does in this case, so it's going to get a 2 negative. And then what would you assign for lead? 2 plus, right? Jaden, oxygen.
0.
All right, everybody, this oxygen, 2 negative, this lead, 2 plus, and then oxygen over here, and sulfur, 4 plus, good, because you have 2 oxygens here. So who's actually changing? Lead is, oops, sorry, not lead. Sulfur is changing to what? To 4 plus, okay, so oxidized or reduced? Okay, so it's oxidized because it went from a -2 and it lost how many electrons? 6 electrons, okay? So I'm just going to put 6 electrons there. And then who else was affected by oxidation reduction? Oxygen went from 0 to what? -2 there and another -2 here. So this is called a disproportionate redox reaction because, actually no, not right term. No, sorry, I'll hold that term for later. This is just the reaction where your oxygens are splitting, and so they're still in the case of going from 0 to -2 or 0 to -2. Both cases they are what? Oxidized or reduced? Reduced, right? And then overall, this single or 2 diatomic oxygen to 1 here and then 2 here. The 1 here gained 2 electrons, and then 2 over here individually gained 2. So it's still 6 electrons being exchanged. Okay, but a disproportionate redox reactions where one compound is both oxidized and reduced. We'll get to that later. Okay, so overall, which agent, the whole entire compound, was oxidized? The sulfur one was oxidized, right? So the PBS, so lead 2 sulfide, was oxidized. So is it an oxidizing agent or reducing agent? Reducing agent. And which compound was reduced? Oxygen. And oxygen being reduced makes it the oxidizing agent. Okay, one thing to note here is that when you write the agents out, if it ever asks for the full agent, it does mean the entire compound where that process of oxidation and reduction occurred. It's not just the individual element. Like you'll notice I didn't write just S, I wrote PBS to write the whole compound. And second note, agents are only reactants. You can never assign a product to be an agent because it's not the one forcing oxidation and reduction. Okay? All right, now we're going to actually get to the balancing of oxidation state. Here we go. We're going to skip that video for now. All right, so these are the 3 styles of balancing, and I know you can balance a reaction. I know you can, but sometimes when things have, like in the alum lab where it has 6 to 10 things, reactants and products, balancing gets pretty tricky, and you go back and forth and back and forth. So these are methods to balancing when you have the opportunity to assign an oxidation state, or you have something that says in acid or in base. You want to balance it like this. So it's just extra balancing methods in your pocket so you can use them when you need them. I'm going to take a minute here, and I will just take a picture of this first, or I'm videoing too, but you guys are going to have these steps memorized by the time we're done today. And my people I told you to test today, during class, I have multiple choice ready for you, or you can make accommodations if you're not during everybody right now, write down those steps for yourself. So you guys are writing down your steps, or at least reading them for clarity. Alright, so when we're looking at oxidation state balancing, it's kind of what we've been doing. You assign all the oxidation states to everything you can. So check. You look for the things that changed. You're looking for ones that were oxidized and reduced, meaning their oxidation states changed. Once you've found out who's changed, you're computing how much they changed by. So you're looking at the overall number of electrons that were exchanged. That's kind of what we were just doing in the previous example. Now, every example I've given you so far, the electrons have been balanced. We counted 6 and 6 in the last one, 2 and 2 in the first one, 1 and 1. We could see they were balanced. And that's because I already have the coefficients balanced for you. So in this case, we're going to make the electrons lost equal to electrons gained by using temporary multipliers or coefficients just for the moment to make sure we're keeping charge balanced. So the fact for 5 is charge must be balanced. We're going to continue to use those coefficients as multipliers to make sure everything else is balanced. But once we get the charge balance, half the battle is won. We don't want to effectively change the coefficients again, because then we've lost charge balance. So you must balance the remainder by inspection without changing your charge balance to overall balance the atoms of the reaction as well. So, and this whole process, it will become very natural. It will become a little organic to you here shortly. We do this because sometimes we can't simply balance by inspection. Sometimes we can't. It's just back and forth, back and forth, back and forth, and you'll never get it balanced. So we're going to try an example here shortly. Okay. Can I get a thumbs up? Do you have the picture if you need it? Okay. So here's our reaction. Write this out first. And write it kind of big so you can have some space for like showing your process. And in your head, I'll put you're saying the names of them. So potassium permanganate plus what? Come on, 10 what? 10 2 chloride plus hydrochloric acid yields manganese what? 2 chloride plus 10 4 chloride plus potassium chloride and water. Okay, so step 1, what's it say, Drew? I know, actually, hold on. Step 1, it says write the reaction, right? Or write the compounds out. Step 2 on your board says what?
Assign oxidation state solid.
Drew, I got you next. Okay, so assign oxidation state solid. Here we go. Looking at potassium permanganate, who's our priority? It's going to be fast now, okay? Oxygen gets a -2. Potassium gets a +1, so that's our like oxygen, and then our group 1 kind of collectively together, they both are priority. Manganese gets what? Plus what? +7. So a -2 times 4, -8. There's already a +1 here, so that gets me down to +7. So I must be putting a +7 here on manganese. Okay. Who's priority here? Chlorine gets a -1. Tin gets a +2. Okay. HCl. -1 and +1. Okay. Manganese. 2 chloride, who gets the priority? Chloride gets -1, manganese get a 2+. Keep going. -1 on chlorine and +4 on tin. I'm hearing some people mumble, but I think you got it. Keep going. -1 and +1, and then water over here. -2 and +1, right? There's 2 hydrogens there. All right, so write the reaction, assigned oxidation states. Qui, what's our next step? Okay, look, and now I want you guys to tell me who is changing oxidation state. Manganese goes from a +7, so draw your brackets, to a +2. Okay, we'll get to the what that is in a second. Who's the other change? 10 from 10-2 to 10-4. Nothing else changes, right? And that's because they're just chilling. They're spectator ions, some of them, and so they're just kind of on it just to make the compound neutral. They're going to be floating in solution if this were a solution. Okay, so we've identified the change. Now what's next? Okay, so let's figure out how many electrons were lost and gained. So manganese went from +7 to +2. Oxidized or reduced? Say again? Loud and proud, people. It went from a +7 and then it went all the way down in charge to +2. Oxidation is loss of electrons. If I lost electrons from a 7, I could go into +8, +9, +10 because my electrons are negatively charged. So this is what? Reduction. How many did it gain? How many electrons did it gain? 5 electrons were gained. Okay. You got me now? You have to talk oxidation through yourself, oxidation reduction, because when you think reduction, you're like, oh, reduces in number. No, reduces in oxidation state. Sorry, 10. How many electrons were gained? I mean lost. So +2 to +4, oxidation is lost, and we lost 2 electrons. Are my electrons balanced? No. Cassie, what's our next step? Okay, so we're going to make some multipliers to serve in our feet to balance electrons. So what we will do here, I'm going to draw this in a different color, is I want 5 to equal 2. Well, how do I get 5 to equal 2? I do not say 2.5. How do we multiply 1 by 2 and 1 by? Okay, so I want to multiply this top one by 2. I'm going to multiply this bottom one by 5. So overall I have 10 electrons exchanged. So the 2 is going to go to the bracketed items. It's going to go to a 2 coefficient in front of potassium permanganate and a 2 coefficient in front of manganese 2 chloride. The 5 is going to go to the what? The 10 2 chloride and 10 4 chloride. What I have done right now is I have electron, I'm trying to say this, I have charge balance. What I have right here is I have charge balance, and I really, really don't want to mess that up. Now I just want to go farther to balance the mass, or balance the atoms that have not been balanced yet. So let's check this by hand. This is what we're calling balance by inspection. Potassiums, are they balanced? No. Okay, so I can add a coefficient here because it's not in the bracketed items. It's not affecting oxidation reduction. It's not affecting charge balance. I'm adding that coefficient just to balance the potassiums. Are the manganeses balanced? Yes. Are the oxygens balanced? How many oxygens on this side? 8 oxygens on this side. Looking over here, I have what? How many here? 1. So what do I need coefficient-wise? I need an 8. Okay, some of the numbers get big, and you're like, whoa, I don't know if I should be putting that, but you should, okay? So we balanced our potassium separately. We balanced our oxygen separately. Our tins balanced? Yes. Our chlorines balanced? Total chlorines over here? How many? So 5 times 2 is 10, plus 1 is 11. So we have 11 chlorines over here. How many chlorines over here? Add them up. 26. Okay? 26. So we've got 4 plus 20 plus 2. 26 electrons. 26 chlorines. So make it happen. Don't you touch the bracketed items. What do I need there? Say again? So there was already 1 there, but I need to account for that whenever I'm balancing. So actually we'll put a 16 here, right? So because that's including that 1 that I already had. 16, you're like, I've never put a 16 on anything, but you will on some of these. So I have 16 chlorines, so that totals up over here is 26. Check with chlorines. How many hydrogens? 16 and 16. Drop pencil, you're done, right? That is oxidation state change. We went through 1, oxidation state assignment. 2, look for what? Look for who was changing, right? We said who's being oxidized and who's being reduced. And with that, we accounted for the number of electrons that were exchanged. What if the electrons are not balanced already? How do you make them balanced? Okay, so put a temporary coefficient as a multiplier to make the charge balance. Once your charge is balanced, by putting the coefficients where the bracketed items are, What do you do next? Say again? Balance the rest of them just by inspection, just by counting like we always do. Yeah. If there were 2 lost and 2 gained, mine will probably be 1. Yeah, so I just put a 1 as a coefficient. All right, so we're gonna let's do like one of these together again, but I'm gonna tell you where they are on your practice. I'm having these actually. This is on your packet. It says AP chemistry balancing redox by change in oxidation state. Go down to the B section, and I want you guys to do 1 and 2 right now. Do 1 and 2 right now, and I'm going to do acid balancing here in a couple weeks. So there's no way in Hades you're going to put this on this paper. This is just for your reference. Please write this in your notes in place, okay? You guys will just have your active reading guides just out so I can see them. I appreciate it. If you can check your first one at least, you have to be on the board for me. Alright, double check questions if you need it, and then we're going to acid balancing. What I specifically want you to do for practice or more of this, basically tonight's homework is two problem sets, that's just like some memory questions. Do number 3 through 7 on the more practice. Do you guys see that below B on your, where you were just working? This is more practice by balancing charge and oxidation state. Yes? Okay, does your number 5 say skip? Yeah, okay, just making sure. Do 3 through 7. Don't skip 5. Try it out. It was hard, but it's not that hard. 3 through 7. Okay. Right. Can I move on from here? Yeah. Okay. So coefficients. If you just write a little key to yourself on the side, 1 3 1 3, because it's in the order that you have, and the first top one is 2 3 3 2 1. And I'll give you a chance to double check those. And I'm videoing too. You can always scroll to this minute here in time. Okay, there's a lot of practice for those, but that's overkill. You only need to do a couple of them to feel comfortable in what you're doing, okay? So, this next idea, I actually prefer much more to what we were just doing. This is more common. It's called balancing an acid, or acid catalysis. So just kind of do a new title, oxidation and reduction reactions in acid, or redox in acid, okay? We're gonna do base probably tomorrow. So the idea is that this is just a sample reaction. Please do not write this reaction down. What you have seen maybe in the past, or you've heard something like this before, you've seen reactions, and then above the arrow, it'll say H plus catalyst, or H plus meaning an acid serving as a catalyst. What does a catalyst do for a reaction? Speeds it up, okay? We will actually have to do this, because sometimes reactions take a long time, and they just sit, and we don't see anything happen. So we actually have to catalyze them with addition of like a strong acid to force the reaction to occur at a reasonable rate, so we can see it happen over time. So it's just, that's it. That's what we're doing. Balancing with the presence of an acid. Here are your steps. Again, take a picture and then you can finish working. I'm going to elaborate on these rules as we go, okay? So you usually have a full reaction, but we can't really work with a full reaction when we're balancing an acid and base. We divide them into the two half reactions. One is the Rig one, and one is the oil one. One's the reduced one, one is the oxidized one. Within those two half reactions is what the terminology is, half reactions. You actually first start with balancing things other than H's and O's, because water is always present, so we try to save O's for last. And we have acid. Acid has an H plus in it, so we don't start with that because it would make it a little bit more complicated. So we balance things like coppers and irons and sodiums and chlorine. So we try to balance the things that are non-HOs first. Then, if you have more oxygens on one side than the other, you add water to first start with balancing oxygens. And you can add water on both sides. Either way it works. You just have to balance your oxygens. Then, so this has to be the first step, like after this. Then you can add an addition of H plus, see the plus one charge. You will make sure you include that as a charge part. You do that second because we're in acid, so you have freely available H pluses that you can utilize to show the balancing of a reaction, just because it's freely floating in acid. Once you have your atoms balanced with H's and O's, you then actually add up the charge on the reactants and the charge on the products, and if the charge isn't balanced, you have to add electrons. The charge will never ever be balanced initially. It will not. Because your job is to show where electrons are being lost and gained. You must be writing electrons on the reactants on one side and the products in the other half reactions. Once you have your charge balance, you will then add coefficients to make the electrons lost and gained equivalent. And I'll go through a whole demonstration of this so it's not bad. At the very end, once you have your charge balanced and your mass balanced, you just sum the two reactions on top of each other, and that will be your full reaction again. So you add the reactants together and you add the products together, and those are your new reactants and products. But you must simplify by canceling the things that are the same on both sides. So if I have 8 waters on one side and 8 waters on the other side, well, it's a wash, right? There's no waters anymore, so I can cancel them both. So I'm going to go through an example of this. Make sure you write down your example with me, okay? All right, so this is like my simplified version. This one's a little bit more complex, but I just orally said some of this, so I can go back to this as needed. But it's just a little bit more complex to give you some depth to what these steps mean. Okay, so don't worry about this just yet. All right, so here's our sample. I promise. Okay, here's our sample. Write down your full reaction first, just so you have the context of where this is occurring in. So potassium dichromate plus iron 2 sulfate yields chromium 3 sulfate plus iron 3 sulfate plus potassium ion. So this would be like what you actually added together in the lab, and you could see a reaction happening. Soon we'll learn how to predict these products for these. But what's actually happening is sulfate's not changing. You can see sulfate from one side to the other. It's exactly the same. And I know you see potassium here, and then you see potassium ion over here. Well, technically that's potassium ion too, right? If this were like an aqueous solution, this would be able to separate as a soluble salt. We would have potassium being spectator and sulfate being spectator. So that's why I've actually excluded them here. And many times you'll actually get this as your starting point, not this, but I just want you to know where this is coming from, because ions are not freely available. Ions come in compound form, which is why chromate was with potassium originally, and iron was with sulfate originally, and so forth. So this is what you would initially probably see. And you guys can obviously see, like, who's changing oxidation state? The iron for sure, like iron 2 to iron 3, right? So that's an obvious one. Who's the other one? Chromium, right? So what's oxidation state of chromium here? Try it out. Plus what? Should be plus 6, right? So this is a -2 for the oxygen. -2 times 7 is -14. Something times 2 is equal to, something times 2 minus 14 is equal to -2. So it's a plus 6, because that essentially has to be a positive 12, and the -14 together make a -2 overall. So positive 12 for the chromiums together, -14 for the oxygens together, equal to -2 overall. So you can see the 2 changes, but that's not really the part that you're whittling down to in detail yet. You now want to break these into half reactions. So the chromium and chromium goes together. Okay, I've already started balancing some of them, but I'm just going to let you guys see that now. Chromium and chromium go together. So the dichromate yields chromium 3+. So dichromate yields chromium 3+. The other half reaction, so ignore this 2 for just a hot second. I don't have like animations to do this here. The other half reaction is the other half of the reaction. Iron 2 going to iron 3. So step 1, half reactions have been written. What was step 2? So balance non-H's and O's. So I've done that here. There's 2 chromiums on this side. I needed 2, so I put a coefficient of 2 in the front. And the irons, there's 1 and there's 1, we're good. So now we go to balancing what? Oxygens, right? So I see in the first half reaction, you just consider them in 2 separate ideas, okay? So you have your 7 oxygens here. What do I need to add to make 7 oxygens over here? 7 waters. So sometimes I start in the middle of my paper on these, because you're going to be adding things to left and right, so that you kind of have some space that you need. So the dichromate yields 2 chromiums because of the 2 coefficient that had to be added, and now 7 H2Os to get the 7 O's handled. Then what do? I can now add hydrogen ions to balance the hydrogens out. How many hydrogens on the left? 0. How many hydrogens on the right? 14. So I'm going to add how many over here? Say again? No. So I've handled the 7. I'm sorry. I've handled the oxygens. Don't touch oxygen again. Now moving on to the hydrogens. So I'm adding 7. Adding 14 H pluses. Okay. So once I've done my non-H's and O's, and then I add my waters to balance the O's, and then I balance the H's with addition of H plus. So now all the atoms are balanced here, right? How about here? Atoms are balanced, right? There's one iron and one iron. No need for oxygens, no need for hydrogen ions. Nothing else is needed on that second half reaction. Okay, so what we've just done here, I got here for you, okay? So let's keep moving down. What was the next step? Balance the charge. Okay, so here's what you have to do. You have to count. On this side, what's the total charge? 14 pluses and 2 negative, total charge. Plus 12, right? So it's a positive 12 charge overall. What's the overall charge over here? Not plus 3, there's 2 of those. Plus 6. You do have to watch those coefficients, they sneak up on you. So overall, I've got a plus 12 charge and a plus 6 charge. I'm going to add electrons. Electrons will bring charge down. So do I want to add electrons to the 12 or add electrons to the 6? To the 12. And I want to bring that 12 plus all the way down to be equivalent to 6 plus. So how many electrons do I need to add to 12 to make it 6? 6. So I'm going to add 6 electrons over here. So I'm adding 6 electrons to the higher charge to bring it down to the lower charge. Okay, same story. Total charge on this one. 2 plus, total charge over here. 3 plus, which side do I add electrons to? How many do I add here? 1 electron. Those are the easy ones because the charge is right smack in the place. All right, so we have 6 electrons on this is the reduction half reaction, and we only have 1 electron on the oxidation half reaction. I need those electrons to be equivalent to follow the law of conservation of matter. What do I do now? Multiply the iron 1 by what? Overall, the whole reaction has to be multiplied by 6 to get this 6 electrons equivalent and to keep the overall charge balance occurring here. So what I've done now, here we go. So we've done this to add 6 electrons. We've multiplied by 6 to get to the electron balance. Now all I do is add these reactions up. And I stack them on top of each other again to add them up. So here's what that looks like. So I've rewritten the blue one here and the green one for you. But what you do is you pull all the reactants down together. So 6 electrons, 14 H pluses, a chromate, and 6 irons, because we added a 6 there, yields 2 chromium 3 pluses, 7 waters, and then whatever was here. 6 iron 3 pluses, and 6 electrons. So this is the non-simplified version right now. I've just kind of pulled all the reactants and products together. What do you guys notice is the exact same on both sides? 6 electrons and 6 electrons, right? We're canceling those out because we should never, ever, ever have excess electrons at the end, assuming that the same were gained and the same were lost. So they have to cancel each other out. And actually, there's nothing else to simplify because there's no extra waters on one side than the other. They're basically, they have to stay the way they are because there's nothing else that's same on both sides. So the canceled and simplified version is right here. Ooh. The board has a delay, my bad. Right here, right there. Okay, take a second there and absorb questions. Right here, that one. So because the 6 electrons that were gained did not equal the 1 electron that was lost, I had to make the electrons equivalent. So I use a multiplier across this entire half reaction to get that there. Okay. All right, so we leave in just a couple of minutes. So I want to make sure you got one good example down first, okay? So here's what I want you to try on acid balancing. Ready? I'll say these. I'll actually write these down here. In the acid balancing, which is the upper right-hand side of the page, under the B section, try 1, 2, 5, and 6. 1, 2, 5, and 6. And if you can do those, you're going to be great, because there's really no more than what we've been doing. So under the oxidation one, you guys are doing 3, 4, 5, 6, 7, 5 questions. And under B, on the acid one, you're doing 4. So they have 9 overall attempts at balancing. All right? And I had been putting on the board 2 days now. If we can try to collect that rest of that alum data, which is just the filter paper with the barium sulfate on it, you guys just need to finish collecting your data you can so you can do an analysis on that. If you can have it done by Friday, I would love to write down notes so we're really quick. If you can't, I can wait. Like, no skin off my back. I just need to get this graded before quarter ends. Okay? They should be to me by Friday, but if for some reason you can continue to. All right. We should be leaving in a minute, guys. How did you guys feel about balancing? Wild or good? It's a lot of steps, okay. After you practice